center of zero velocity, and we'll see how we can use that particular thing, the instantaneous center of zero velocity, in order to simplify the math which we do to solve the problems. So this section is on instantaneous. Okay, so if there is a rigid body and that's a point A, or let's call it B, and A is another point. So what we have done in the last lecture is written down the velocity of B as velocity of A plus omega cross R B with respect to A. So there is a point, it could be outside the body. Let me put it right. Which has a velocity of 0. Okay, that point is called the instantaneous center. So this is IC. Zero plus omega R B with respect to IC. So what we're interested in is how to find that point IC, because if you can find the location of that point IC, then you can, so you know R B with respect to C, and say you know the velocity of B, then you can find omega, which is the angular velocity of the rigid body. I'm doing a mistake here, this should be cross. Okay, find this using trig usually. And then if you know that, as I said, you can find omega. It's the same omega which comes over here. Except now, when you write this formula, you do not have to write the velocity of A. So it's somewhat simpler. You trade off having to compute A with the work done in trying to compute the location of this point IC in trig. And this will become more clear when I do problems. Okay, so I'll give you some examples of IC. And these are sort of obvious examples. Then I'll show you how to find the ICs for a system of rigid links. So if it's a rolling wheel, what's the point which has zero velocity as the wheel rolls? Center is not, no. It's this point. This is the IC. Because at any instant atom it's at rest. The center point cannot be the IC because it has a velocity in the horizontal direction, right? Omega times R. If I give you a pinned link with a pin, what's the IC? Pin joint, where this can move, it can spin. Okay, it's basically this point is the IC. Why it's the IC is because that point doesn't move. Velocity of IC is 0.
So IC when it's not moving?
It's the point which does not move. So when a rigid body is rotating, you got to find the point which doesn't move, which has 0 speed. For this point, it so happens that those points are on the rigid body. Okay, so this one might be a harder one. If there's a link, it's not fixed, it's translating. What it means, it's moving with a uniform speed. It's not rotating, it's just translating. Where is the IC? No. The center would have a velocity of, let's say this is moving with a velocity of v, right? The center would have velocity of v. So it's not 0 velocity. No, it's actually at infinity.
Which
It's could be this side, that side, but the velocity. So when things are moving in, when things are translating, the velocity of the IC at infinity. There is an IC, just that you'll have to go to infinity to find it. Well, it makes sense because remember what the IC does. It basically tells you if you're given the motion. If we write it this way, V equals omega times. Let's say this is a point A. Okay, R A with respect to IC. Right. I just wrote the magnitude. I have not written the direction. Right. I have not written the vector. So V, we know it's translating. Where is this quantity? This is at infinity. Right. That's what I told you. That's only possible if V is finite. This is infinity. So if you have on the left side you have a finite quantity, on the right side you have infinity, then omega has to approach 0 in order for that product to be infinite, which means that omega is 0, which is really the case. It's not rotating, it's translating. So when things are translating, the IC will be at infinity. However, we will never see a problem where IC is at infinity. This could only be a question in, like, be a short answer question. Just wanted to tell you.
Could you explain just really quick about the IC for rolling wheel?
Yes, when a wheel rolls, any point is moving with a speed. This point is moving, in fact, in a straight direction, in a horizontal direction, given by omega times r, right? The only point which is at rest, which is not moving, is this point. It's not slipping, so it's rolling. So that has to be the IC. Velocity of this point is 0. Okay, so that was two cases where the IC was on the rigid body, and that was a case which was at infinity. I will show you an example where, I'll show you how to compute the IC for a rigid body, and that's what we will see most of the time in this course. So given VB and VA, find IC. Okay, so given the velocity of 2 points on the rigid body, and you got to find the IC. So the method is actually pretty simple. All you got to do is draw a line at right angles to the velocity. So draw a line at right angles, and the point of intersection is always the IC. So that is how you locate the IC. Pretty much find the points of, whose velocity you know, and then draw right angles to those velocities. Point of intersection is the IC. So this will give you get R A with respect to IC, which is this vector, and then get R B with respect to IC. So if you know that, then velocity of B, and I'm only going to write the magnitude, is omega times RB with respect to IC, and velocity of A is omega RA with respect to IC. So if you want to find the angular speed, you can use either expression. You could use this one or this one. So if you find, if this is given, you evaluate this. How do you evaluate that? Well, you draw right angles to the velocity vector, find the point of intersection, and that's how you get RB with respect to IC and RA with respect to IC. So once you know this, you can easily find the angular speed. And that's the trick. You do not have to use the formula I had shown last time. Remember, I showed you Vp is Va plus omega. You can use that if you're not following this path. So again, will be clear when I solve a problem. So that's pretty much it. Yeah, question? Yeah, I just wrote the magnitude here because that's what is most important here. We just want to find omega, direction of omega. Right, so you can see that the direction of velocity and direction of omega is, so what is happening is the body is rotating about the IC, and so by just visualizing how the body will move about the IC, you can figure out the direction of omega. It's basically counterclockwise in this case. The velocity has been swapped to the other side to move clockwise. Okay, so the best way to make this clear is to solve some problems where you are asked to figure out the ICs. Okay. So let me tell you one thing. You are going to get a question on IC in the exam. It might be a short answer question, it may be a long answer question. But you are going to get it. Yeah.
I was wondering if you put the homework assignments together yourself, what are some of the questions you were sure before?
Sure, I'll follow the last part.
If you put together the homework yourself instead of having it, what are some of the questions you might pick out?
Same question. Just that I have to go and grade them, which is very hard to do with the class. Well, for 40 is not hard, but 180 is hard. I'll pick the same questions there. You have picked them. I think we pick them, all of us pick them together. Okay, so every rigid body has an IC. Okay, so in this, the first example, we have A, B, and there's another crank, which is the one which is shown with angular speed omega. That has an IC too. That's key. Every rigid body is an IC. So this rigid body is an IC, this rigid body is an IC, and this one will have an IC too. Okay. You're asked in this question to find the IC of link AB only of this link. Okay. In order to find the IC of any link, you got to find the velocity of 2 points. So clearly those 2 points are this and this. So velocity of, what's the direction of velocity of A? To the right. So it's going to be, as I said, so what you've got to do is to find the velocity of A, take the vector from 0 to A and turn it in the direction of omega by 90 degrees. So it's going to be pointing this way and it's going to be 90 degrees to the vector. So it's going to be the same thing which I showed you some time back. The short question which I put up earlier. So that's the velocity of A. It's always 90 degrees to the body. What's the direction of velocity of point B? B is sliding. So you pretty much know it's going to be this way. It's along the inclined plane, right? Okay, so you know the velocity of 2 points, so then draw the line normal to those 2 points. So in this case, this is going to be one of the lines, this is going to be the other line, 90 degrees. This is the IC. Okay, so you might have a question where you might be told to draw the IC, or you might be told to find the distance of the IC from A. So you can, if you're given this length, actually, if you're given this length and this length, you might, and of course this angle, I think, then you can use the fact that this is a triangle to find the distance B to IC and A to IC. I'm not doing that now, but next question I will.
So what was the origin of this shape?
Can you say that again?
The origin, did you find the velocity with respect to origin?
Yeah. So I need to find the velocity of point A. Okay, doesn't matter how I do it. So the way I found the velocity of A is I use this link, not this one, but this link, and I know that link is moving with the angular speed omega. So I use that fact to find the velocity of point A. So I did not use anything about AB to find the velocity of A. I just used the fact that the link I just highlighted here has an angular speed that way.
But I mean, you don't do it with respect to any coordinate system or anything like that.
That is how it is, right? It is, what I care is there is in my mind there's a coordinate frame which is I is that way and j is that way, except that if you are trying to, in this case, you're just trying to draw it. If there were angles there, then yeah, you have to write those angles and how to find out distances and so on. In this case, you're just supposed to draw it. It's not important to show I and j. So as long as you show it's along it's 90 degrees to that PA. So the way we grade this is we'll see if you got this vector right, we'll see if you got that vector right, and we'll see if you drew it at 90 degrees. As long as you show that's good.
So no numbers involved.
No numbers in this question, but yes, we're going to come to a problem where there'll be numbers, and then you have to use trig. Okay, so moving on, what's the IC of link AB? Okay, as I said again, you need to find the velocity of 2 points. And the simplest points are probably A and B. So B is this way. I think it's going to be that way. Right? B is going to move to the left because the disk is spinning clockwise. So counterclockwise, my bad. Counterclockwise. So B is to the left.
Is it B fixed?
Okay, so
Yeah. But it fits to the can or whatever that is.
okay, the circular disk is fixed to the point A with pin joint. The slider is fixed with a pin joint. This can roll on the surface. When this rolls, this slides. See, I'm not. When this goes this way, I think it's going to roll, right? Yeah. So this has to be. I think we would be fine if you. We shouldn't have a problem if you drew the velocity that way and start answering it. We would not penalize you. Okay? As long as you show your methodology is right, that is how you find the IC. So we found the velocity of B. Let's try to find the velocity of A. How do you find the velocity of A? Yeah. So what I would assume that this wheel is rolling, not slipping. Okay. So this point is at rest. So if this point is at rest, and I want to find the velocity of point A, then the velocity of point A is going to be, well, I need to find this vector, and then turn this vector by 90 degrees in this direction. So it's going to be turning this way. Is that clear? So this point is at rest. I drew this vector, and then I'm going to draw this at right angle.
If that circle was fixed, how could we?
Then it will not move, I think.
Because wouldn't the B kind of like move back and forth?
No, I think it becomes a structure. So if you do, there is a mechanism designed it. If you're given number of pin joints and number of links, then you can find what is known as degrees of freedom of the system. So if it has 1 degree of freedom, then you need to specify one angular speed in order for the whole thing to move. If it becomes a structure, then it doesn't move. It's fixed. So if you fix that, it becomes a structure.
But it's technically rolling this way.
It's rolling that way, right? Yeah. So we'll ensure that we only give you 1 degree of freedom system. So if you thought that was confusing, you do not have to worry about it. It's not part of this course. We're not going to ask you to do complicated problems. Okay, so if you know the velocity of A, we know the velocity of B, that is the direction. In order to find the IC, I need to draw vector like this, sorry, a line normal to B, velocity of B, and then line normal to velocity of B. So this has to be the IC of AB. So draw, once you find the direction of velocity of B and velocity of A, I think they can be wrong.
Wouldn't the normal of A, like wouldn't
That's
the
wrong.
IC ended up being
Yes,
like B?
this is wrong. Hold on, I did it wrong. Okay, so this is right. This is velocity of b, and that is 90 degrees. I need to draw the vector. This is VA. I need to draw the line which is normal to this vector. So it has to be this. So this is IC. Sorry. Yeah.
So you know at the top, to find out the direction of the shape,
Yeah.
we grab the rod and then we just
That's fine.
grab the omega and we did it in that direction.
Yes.
In that bottom left one is different. When we have a rolling one, yeah. When we have a rolling body, we just grab the point that's touching the floor, I suppose, and then we just draw like the vector to the point that we're trying to find, and then we just
That's for this one, right? That's for this one. Okay, so let me not do this problem, but post the solution. I'm running out of time. So do this question, and I don't think I have the time to go through the whole thing, but let's see how far we can get. This disappeared. Okay, I'm going to set up this problem. I may not have the time to finish it. So due to slipping, points A and B on the rim of the disk have velocities as shown. Okay, determine the velocity of the center of point C and point E. Okay, now this is slightly different from the rolling wheel. This is not rolling. This is slipping because velocity of point A is not 0. Okay, so do not make the assumption that this point is rolling. So you have to find the velocity of point C and velocity of point E given this information. So if this one rolls to the right, this point moves to the left. I'm going to redraw this figure. So velocity of point B is this way, velocity of point A is this way, and if I tell you to find the IC, then you do the same thing, which is you draw a right angle, and the IC should be somewhere on this. But you don't quite know where it is. It could be here. So let's say that this is the IC is here. So we need to find the location of the IC, because if we find it, then we can then solve it. So in order to find the IC, let's call this distance x, where x is the distance from A to the IC. And clearly this distance, what's that distance? Between IC and B and A. IC and A. It's going to be the diameter of the circle minus x, right? The diameter is it 1.6, right? 0.8 is the radius, so 1.6 minus x. Okay, now note that velocity of IC is 0. So I'm going to use that fact to find x. So if this is spinning with an angular speed omega, then velocity of B is velocity of IC plus omega times x. Okay, I just wrote the scalar equation instead of writing the vector equation. Okay, but velocity of IC is 0. Similarly, velocity of A is velocity of IC plus omega d minus x. IC is 0. So what you can do is, from this you can see that omega is VB divided by x. So I took this at here, and then it's also equal to VA divided by d minus x, which came from here. So no, IC is the point which has 0 velocity, period. IC is always 0 velocity. Just that I do not know the location. By the way, IC is not at C. Okay, it is not at C.
Could you say that it would be at C if V and UV have the same velocity?
Yes, that's right. In the opposite direction, yes. Okay, so omega equals, what's the time? Is 9:50 already? 9:49. Okay, let me finish this. 9:49. Okay, I have 11 minutes, right? Okay, I just have 1 minute. Velocity of B is 10, x is unknown. Velocity of A is 5, d minus x. Sorry, I'll call this 1. This is 1.6 minus x. 1.6 minus x. Okay, so 10 equals omega x, 5 equals 1.6. Equals omega times 1.6 minus x. So two equations, two unknowns. So you can solve for omega. It comes out to be 9.37 radians per second, and x is 1.067 feet. Okay, so I solved for omega and x, but I've still not solved for VC and VE. So VC is VIC plus omega cross RC with respect to IC, and then VE is VIC plus omega crossed RE with respect to IC, where this is clearly 0. All I got to do is figure this out, and then I know what omega is. Omega is already evaluated, right? So I can find velocity of C and velocity of E. So I'll do that and post the notes. I am going to have so I'm not going to have officers next week. I'm not here, but I will have officers right now in my office. AET 2.338. Feel free to come by. Right now, 2.338. AET 2.338.
So no class?
There is class. Please come to class. There's class on Monday and there's class